Friends, the purpose of this short video is to actually talk to you about a question that I have been receiving from many quarters about the different types of enhanced monofocal IUL or EDOF IULs that are there, and that would help and how do they work actually. So I have written about it in my blog quickguide.org, and you can always go into the optics section over here. So if you click in the optics section, you could actually go into these two articles over here, Guide to Extended Depth of Focus IUL Optics. Now in this article I have actually defined what do we mean by depth of focus, and to qualify as an extended depth of focus IUL, what are the US FDA regulations. Say for example, you can go through these 3 points over here, and it says that clearly that 50% of eyes achieving monocular distance corrected intermediate visual acuity of better than or equal to 0.2 logMAR, which is around 20 by 32 at 66 centimeters, right? And then I actually explain how do these different IULs provide your patients a depth of focus. For example, lenses that have a change in asphericity from the center to the periphery. So change in, and they commonly use the term that, adding spherical aberration, and that's basically the Ray 1 EMV, for example. The second category of lenses actually that have a higher radius of curvature or an extra bit of power in the central 1 millimeter of the lens, and that is actually the Eyhance. Now beyond these two lenses or two ways of providing the depth of focus, there are also other ways of providing the depth of focus, and that actually is related to the ISOPURE and the Impress, and they don't add actually spherical aberration on the IUL optics or a spherical power on the IUL optics, but what they do is actually they kind of provide something like an higher order polynomial, and I will explain that, and it is actually explained in this article what is meant by that. So standard aspheric curvature changes cannot actually define what ISOPURE and Impress do to provide the patient's depth of focus. So you can actually follow this article over here. So lenses that provide a change in asphericity, that is adding a spherical aberration over here, and lenses that actually provide a higher radius of curvature or a spherical power in this central part of the lens. So this is how you can actually differentiate between the two. If you talk about the techniques in the central 1 millimeter, in the central 1 millimeter actually they add a spherical power, and a spherical power to differentiate from what Ray 1 EMV does, actually adding spherical aberration. What they say, if I have to actually kind of break it down, that would mean that while with the Eyhance, the radius of curvature will be the same in the central 1 millimeter that provides the depth of focus. For the Ray 1 EMV, the radius of curvature will not be the same that actually is providing you the depth of focus. So that is basically the difference between the two lenses over here. And then I go on to talk about the ISOPURE and the Impress, and how the ISOPURE and Impress provides the depth of focus is through an higher order optics or higher order polynomials, and this typically is defined by inflection points over here. So for example, the Impress in the central 2 millimeters will have inflection points. So what is an inflection point? Inflection point means, if you think of the share price of a particular company is growing, right? On Monday it goes up, on Tuesday it goes up, but on Wednesday suddenly it is actually coming down. So where it actually goes up and comes down, that particular point, we call it as the inflection points. So inflection points, in other words, means a change from the concavity up to a concavity down. So this part is actually the concavity up over here. This part is the concavity up, and this part is the concavity down. So a pencil ray of light goes through the concavity up, actually falls before the distance focal point. The distance focal point is a function of the standard aspheric curvature, and which is actually denoted by the green part over here, and the concavity down. So when the ray of light actually goes through this concavity down, So what you see over here is that, you know, it actually pushes the light rays a little back. So you actually go, you know, at the back of the focal point, than where the rays of light from the standard aspheric curvature is focusing. So that is how it is done actually. And you can go through this entire article over here, and it might make some sense. And you know, before you go into this article, I would also like to talk to you about another article that actually provides you a basic understanding of you know, how the higher order optics like the ISOPURE and the IMPRESS works. Or maybe the you know, this article may be also good for you to understand you know, how a spherical lens is made and an aspheric lenses are made, and how the freeform lenses, that is the IMPRESS and the ISOPURE, is different from a standard spheric and an aspheric lenses. And this article actually again in the optics section over here, if you click over here, this is the article spheric, aspheric and freeform lenses. It kind of helps you understand that you can actually define a lens through its conic constants. Conic constant is what? When you have two cones over here facing each other, and you take a knife, you can actually get various shapes over here. You can cut it in a circular fashion. That actually means the spherical part of, if you take the cross section of a circle, it's actually the spherical part. You can have a parabola, you can have an ellipse, you can have an hyperbola, and they're all defined by the conic constant. You know, for example, a spherical lens, for example, the Alcon's is a 6080, or the Hoya's 150 is not an aspheric lens, it is a spherical lens, and the conic constant of such lenses will be 0. However, if you have a lens which is absolutely aspheric, for example the INVISTA lens, where it does not add to the positive spherical aberration of the cornea, it is a zero spherical aberration lens, then it would be a parabola shape, and its conic constant will be 0. Its conic constant will be -1, the 1. So this is actually how you define the conic constant defines the safe or the surface curvature of the lenses over here. So the conic constant of a spherical aberration would be 0, the conic constant of a parabola would be -1, and between the two there can be different shapes of the lenses over here. But for a freeform lens on which the ISOPURE and the IMPRESS is designed, is actually not having a conic constant for that particular you know, surface area where it is actually providing you a depth of focus. And what it has is an inflection point, that is a concavity up and a concavity down here. So you cannot define these lenses by a standard aspheric formula. So it is actually made up of higher order polynomial functions over here, right? So you can actually go through this article over here that actually provides you some understanding, a basic understanding of the difference between a spheric lens, an aspheric lens and a freeform lens. And then you can go to this article, the guide to depth of focus lenses, and then you will have actually an understanding of how this you know, extended depth of focus lenses actually work, you know, the different ways of providing the EDOF lenses, right? So thank you. I hope you find this article, this short video useful, and you can always go into my website quickguide.org to you know, browse and use the search button to kind of, you know, understand, to look for what you want to look for. I would highly recommend, if you are interested in EDOF lenses, to go through these 2 articles. Thank you.